Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 37th lecture. In this lecture, we will be discussing chip planning. In the earlier lectures, we had seen that the physical design task is broken down into multiple smaller tasks, and among them the first task is chip planning. So, in chip planning, we basically do the planning for the physical design or the layout of our circuit. So, now chip planning is also a complicated task, and we break down into further steps. So, the first step is related to hierarchical design implementation. So, typically for industrial design, we implement our physical design or layout using hierarchical design methodology, and therefore, we need to do certain tasks such as partitioning and so on, and that becomes the first task for chip planning. And then comes the task of floor planning, in which we place bigger objects on our on the die and carry out other certain important tasks related to where the object should be on the layout, and then we do a power planning. So, these are three major tasks that we need to carry out during chip planning. So, in this lecture, we will be discussing hierarchical design implementation and some aspects of floor planning. And in the next lecture, we will be discussing floor planning in more detail, and we will also be discussing power planning. Now, before moving to the chip planning, let us look into a quotation from Lao Tzu, who is an ancient Taoist philosopher, right. Now, this statement is very old, but is still very important in terms of planning. So, the statement is, while times are quiet, it is easy to take action. Or before coming troubles have cast their shadows, it is easy to lay plans. A journey of 1,000 miles began with a single step. Though it is a very old saying or statement, it is very much relevant for VLSI, right. So, when we are doing actually chip planning, when we are trying to do some complicated task, then what is the suitable time to lay our plans? So, the most suitable time is at the beginning, when the times are quiet, right, and therefore, and before things have become bad, we do a good planning for our chip or of the layout of our chip, and in subsequent steps or in subsequent design flow, we carry out or implement those plans in small steps, right. So, this is how we should proceed, right. So, why we will want to do this chip planning at the earlier stages of physical design? The reason is that at that time we have not yet decided many things about the physical layout of our design, and therefore, there is a lot of flexibility, right. There is a lot of flexibility, and therefore, the most important decisions related to physical design must be taken at that point, at the beginning of the design flow or during the chip planning stage, right. Because if we take a wrong decision at this point, then that wrong decision will percolate throughout our design flow and it will impact the final QR. So, right at the beginning, when we are doing we are starting the physical design flow, we should take most important decisions related to physical design, and because it offers a great deal of flexibility. Now, let us look into that how chip planning is done. Now, chip planning depends a lot on what is our implementation methodology. like how do we want to proceed with doing the physical design for our chip, right. So, an implementation methodology or physical design implementation methodology are of two types. The first one is flat design implementation and the second type is hierarchical design implementation. So, when our design is very small, right, in that case what we can do is that we can flatten our design. By flattening we mean is, what we mean is that we get rid of the hierarchy in our design. For example, when we have discussed Verilog, we have seen that we write a Verilog top module, inside that we have instance, and then that instance refers to a master module, and within master module there can be multiple instances. So, we have a design hierarchy. So, what in flat design implementation is done is that we get rid of the design hierarchy, and in the top level design we have only the standard cells. We have standard cells. So, whatever was contained in the instances and their master modules, we get them, or we take them and instantiate directly at the top level, right. So, at the top level we will be having only, at the top level of our design or chip, we will have only say standard cells and the instances of the libraries and some hard macros, right. So, everything is flattened out, that is what the flattening is. And then we proceed with physical design implementation or creating the layout for this chip in one go, right. So, this is what flat design implementation is. Now, this method is suitable or is okay or workable for designs which are of small size. But when the design size become bigger, as in industrial designs we can have millions of instances or billions of instances, in that case the flat design implementation becomes too difficult, not only for the designer but also for the implementation tools or the EDA tools that we use. So, in that case, for a big design, when we have multi-million gate design, in those cases we proceed with hierarchical design implementation, which is a type of divide and conquer strategy, right. So, it basically divides the complete design into smaller designs and then implement them and then build the complete design out of it, right. So, in hierarchical design implementation, the major tasks are partitioning, budgeting, block implementation and then top level assembly. So, these are some of the most important tasks that we need to carry out during implementing our design in hierarchical manner, right. Since most of the industrial designs follow this kind of strategy of divide and conquer, let us go and understand that what are these steps: partitioning, budgeting and so on. So, in the when we have got a very big design, very big in terms of number of gates or transistors that it is containing, right. If it is a very large design, in those cases we partition into smaller parts. Now, how to proceed with partitioning, right? How do we partition? One natural way is to partition using logical functionality, meaning that if we have a chip, we think that what part of the chip is doing some function and we group them together, right. For example, if there was a chip and it was doing some, it was containing say CPU, right, and another media processor and some other kind of entities, right, at the top level. Then we can say that at the top level it consists of this partition, ROM, PLL, CPU, controller, power controller, media processor and so on. And then if the block size or if the partition size is still not good enough for us to handle, we further do it in iteratively or recursively going down the hierarchy. For example, we can again partition main CPU to controller, ALU, register bank, and similarly ALU can for example, in another hierarchy ALU can be further partitioned into say decoder, computational unit, multiplier units and a unit which is doing say DCT computation. right. So, given a complicated design or chip which is doing a complicated functionality, we can break down or partition our design into multiple entities based on the functionality, right. So, the different entities that we get, though the different partitions that we get, those are typically known as blocks. So, in this case, for example, at chip level, for this chip, we have first block which is say consisting of glue logic, second block consisting of say shared cache, third block is of ROM, PLL and so on. So, these are various blocks, right. Now, one block can contain another block. For example, in this block main CPU will contain say controller, ALU and register bank, which are further a sub block of the block main CPU, right. So, this is one way of doing the partitioning. Now, there are other approaches to do partitioning. For example, we can group modules into clusters. So, we have a big design which is consisting of various modules. We can group together similar kind of or based on some similarity, we group together some of the modules and create hierarchies of modules, right. That is another way to do the partitioning. It may not be with respect to functionality, but maybe we are just partitioning based on the how much big a block is. Based on that, we are clustering together modules and grouping them together into a same block, right. Another way to partition is using say partitioning algorithm. So, suppose there is a netlist, which contains say 10 million instances, right, and we want to partition it, right. This is now this netlist is a flat netlist, meaning that it is contains only say standard cells, right. This has got only standard cells and but it contains lots of standard cells, meaning that there are say 10 million standard cells, and it is not easy to handle for the tool. For example, so let us suppose that is the case and we want to break it down into say smaller blocks of say 1 million gates, right. So, we will want to create say 10 partitions or blocks for this, right. Now, how to proceed creating partitions, right. So, in that case we take help of algorithm, and these algorithms there are based on say min cut algorithm, right. Min cut algorithm which basically tries to find a partition or cut in our design such that the number of cuts or nets crossing the blocks are minimized, right. This is one way, or this is one of the objective of that can be used by the partitioning tool. So, why do we want to minimize the number of cuts? So, what we mean by cut is that suppose this is a top level design and we had blocks B1 and this block another block B2, right. Now, how many nets are crossing between these two blocks? Those are basically cuts, right, and we want to basically minimize these numbers of cuts. So, why will we want to do this minimization? So, the reason is that because if we minimize the number of cuts, then the making interconnections between blocks or creating or doing routing between blocks, that becomes easy, right. That is the first reason. The second reason is that if the blocks crosses partitions or if in nets crosses partition or block or crosses two blocks or are lying in two blocks, then the timing of that net can become affected or impacted and the delay can increase. The delay can increase because it is going through say from one block and then going through the top level entity and then going again into the another block and so on, and therefore, the timing of that net can be bad. Okay. And the third reason why we want to say minimize the number of cuts is that if we have less number of cuts, then the number of pins that will be in the block say B1, in this case there are 4 cuts and therefore, there will be 4 pins corresponding to each cut in the block B1, right. Now, if the number of pins in a block is less, then the block then the physical design for the block B1 will become easier, or carrying out the physical design or physical implementation for the block B1 gets easy if the number of cuts are less, right. So, and that is why we try to minimize the cut in while partitioning, and then we proceed with implementing each of the blocks, right. So, this is how we can do the partitioning of our design and into multiple blocks. Now, once we have done the partitioning of a design, then we need to do what is known as budgeting. Now, what is budgeting? So, budgeting is the process of allocating some fraction of the clock cycle to different blocks and the top level design for signals crossing block boundaries, right. So, if there are signals which are crossing block boundaries, then we have to allocate a priori that how much time do we allow a signal to propagate in a given block. Okay. So, let me explain this with the help of example. Suppose this was my top level entity. This one was is the top level entity. Now, this top level entity contains 3 blocks B1, B2 and B3. And suppose there is a data path which is starting from FF1, right, from this point, this path. It goes through combinational circuit element D1, then combinational circuit element D2, then combinational circuit element D3 in the block B2, and then into the combination goes through the pins of the blocks, and then reaches block B3, and it will go through D4, and finally it get captured by FF2, right. Now, this FF1 and FF2 are working on a working on the same clock CLK, right. So, this is a synchronous design. Now, if this is a synchronous design, we want that the signal that starts from FF1, it should reach FF2 by the next clock edge, right. Then only it will be able to satisfy the setup requirement, right. So, it means that the signal that starts from FF1's clock pin, right, it should the delay between this point and this point, right, between FF1 and FF2, that is delay shown by D1, D2, D3 and D4 should be such that the signal should reach the capture flip flop by the next clock edge. By that means that the maximum delay it can have is the clock period, right. Now, how to enforce this constraint, right? This constraint must be enforced on each of the blocks, right, because later on we will be implementing each of the blocks separately, right. So, to specify the constraint that B1 must honor, B2 must honor and B3 must honor, we create SDC file or the constraint file separately for each of the block. For example, we will have B1.SDC for this one, B2.SDC for the second and B3 for B3.SDC for the third, and one for the top level will have top level top.SDC, right. Now, in this SDC file that we should have for this block, we should have a constraint which should say that how much time that D1 can take maximum, right. If D1 takes lot of time, delay is very large, then the signal will not reach in one clock cycle to the block B3, right. And therefore, depending on how much delay we expect in expect to be in each of the block, right, B1, B2, B3, we will allocate some fraction of the clock cycle. For example, if we assume that most of the computation for this path is being done in block B2 and say 70% of the delay we expect it to be in this part, right. Then we will write our SDC file such that we allocate 70% of the clock cycle to B2, right, and maybe say 10% to B1 and 10% to this B3 and 10% for the top level. Note that even if top level does not contain any instance, for example, here it contains the instant or the combinational logic D2, even if it is not containing containing any instance, then also we must allocate some portion of the clock cycle to the top level also. Why? Because the top level, when we do routing, the routing might go through the top level and it might encounter some delay at the top level, right. And therefore, we must not forget to allocate some fraction of the clock cycle to the top level entity also, right. So, we create the block level constraints or SDC file, right. So, this is how we convey the timing constraints of that is valid for the top level to the block level, right. So, we are conveying the constraint to each of the block related to timing. But there are other constraints, for example, there can be physical design constraints also. For example, suppose at the top level we are thinking or we are planning that a net should be going from say B1 and it goes through B2 and reaches B3, right. And we are doing some routing at the top level which crosses through or over the B2, right. And therefore, we must allocate some portion of the interconnect at the block level B2, which does not allow the block B2 to utilize that routing resource, right. So, whatever the routing resource constraints are there at the top level, we must also convey that routing resource constraint or physical design constraint to the block B2 also. So, it is not only the timing constraint that we need to worry about that we need to push down from the top level to the block level, but we also need to push down the physical design constraint that may be imposed by the top level to the block level entities, right. And it may be also related to the test or DFT part. For example, if there is a scan chain which takes input in this block B2, right. So, we have to say that where the scan chain will get the signal, meaning that where the scan in port is, where is the scan out port for the block, right. And then this scan out, scan in and scan out can be connected further to other blocks and so on, right. So, the test will also enforce some constraint at the block level, and that also must also be conveyed during when we are creating blocks. Now, once we have created our blocks and we have pushed down the constraints that must be satisfied, we by the blocks we implement each of the blocks separately, right. Different teams can implement different blocks. For example, B1 can be implemented by one team, and B2 may be implemented by another team, and so on. So, while implementing this, what must the block implementer look into is that it must honor the timing budgets that was given that was imposed from the top level, and it also must also satisfy other constraints related to say physical design and test and so on. So, the block level implementation should verify that at the block level all the constraints that have had trickled down from the top level or pushed down from the top level, those are honored. Now, once the blocks are ready, right, these blocks are ready, then we go into the top level. We integrate these blocks at the top level, and then we must need to also verify, right. We must also need to verify that after the blocks are integrated, whether we are getting the correct timing and other violations are not there. For example, design rule violations are not there and so on. So, when we do top level assembly, we need to verify. Now, here the problem comes, right. Now, if we put everything in the block that was there at the top level and we carry out verification, then the complexity of verification at the top level remains the same, because all the blocks view is there at the top level, right. But then what we can do, or how can we avoid this problem, is that we can omit the details of the timing paths contained entirely within the block. Why we can omit? We can omit it because while doing the block implementation, we have already verified that at the block level the constraints are met, right. So, the flip flop to flip flop path which are say contained fully within a block, those we need not verify again at the top level, we can simply ignore them, right. For example, suppose this was our block, suppose this one was B1, right, and this we want to we implemented, right, at the block level, and we want to put it at the top level, right. Now, in this block B1 there are different types of paths. For example, there are paths from this flip flop FF1 to FF2. Now, this the timing of this path has been verified at the timing of this path has been verified while implementing the block B1, and therefore, we did not verify it again, right. So, what we should do is that at the block at the block level, we should only be we should only be worried about the interface path. And what are these interface paths? So, the interface paths are the paths which come directly from the inputs. For example, this is an interface path, right. This is an interface path which goes from input to the output, right, and this is an interface path which is directly going to the output. So, these are interfaces path, and these paths characteristics must be known when we are doing the top level timing analysis. So, when we are doing top level timing analysis, then we need to know the characteristics of the interface paths of the individual blocks in our design. Suppose there was a design top and this B1 was there, this B1 that I have shown here was instantiated here. Now, this B1 can receive signal through this input, right, and and finally to this flip flop FF1, right, FF1, right. So, at the top level we must verify that the delay of this top level entity is not large such that it introduces some timing violations within the block, right, and therefore, we must know the characteristics of the interface paths while we are doing verification at the top level, right. So, we retain the information of the interface timing paths of the block level and we create an abstract model. What is an abstract model? So, in abstract model, we get rid of all the internal paths meaning flip flop to flip flop paths, right. So, now in a typical design, there are lots of flip flop to flip flop paths, right, and therefore, if we get rid of those paths, most of our design becomes very small, or the block becomes very small, and therefore, we are saying that we are creating a abstract view of the block, right, because it is a reduced form of a block. We have got rid of the information which are not required for verification at the top level. And there are many ways in which these interface modeling of interface paths can be done. One of them is using, say, extracted timing model, which is a model using .lib file, right, and the other can be using interface library model, which is based on or which models the interface paths using logic gates, right. So, now that the commercial tools can support this abstract model in many other ways, right. So, I will suggest that please look into the manual that you will be of the tool that you will be using in your physical design implementation. In those manuals, it will be indicated that how abstract timing model can be created for a block, and you can use that model when you are integrating that particular block at the top level, right. Now, what are the merits of hierarchical design methodology? So, the first merit is that the physical implementation and other EDA tools need to handle smaller problems, right. So, if there was a 10 million gate design, we partitioned into 10 design of 1 million, right. Now, EDA tool need to handle only 1 million gate design rather than 10 million, and therefore, the physical implementation tool will be the problem for the physical implementation tools that becomes smaller or get reduced, and therefore, in physical design implementation we can use even those tools which cannot support a large number of gates at the top level. For example, suppose there is a tool which cannot handle, say, 10 million gate design, but that tool is supporting, say, 1 million gate design, right. So, we can partition our design into 10 such small blocks, and then use the same implementation tool, right. So, we can get a design which is, or finally we can get the top level design which is consisting of 10 million gates, which is beyond the capability of the physical implementation tool. And it also actually speeds up the design implementation. Why? Because once we have done the partitioning, then each of the blocks can be worked on concurrently by different teams, right. And therefore, the overall design time of a chip can reduce. Now, what are the disadvantages of block hierarchical design methodology? So, one of the disadvantages is that it is challenging to partition a design optimally, right. Of course, we can design, we can partition our design in many ways, but is it optimal, right? Are we getting the best figures of merit? The answer is that it may not be, right, because the problem of partitioning itself is very difficult or challenging, right. And the second is that we may lose some opportunities of inter-block optimization, right. So, a physical design tool is only seeing the view of a block, right, and therefore, if there are some scope of optimization between two blocks, right, there are paths which are going from one block to another, and some optimization in timing and other characteristics can be done, those opportunities can get missed in this hierarchical design methodologies. Despite these disadvantages, for typical industry scale designs, we use hierarchical design methodologies because it speeds up our chip design process, and it becomes easier for the tool and also designers. Now, let us go into the second task of chip planning, that is floor planning. Now, what is floor planning? So, the floor planning is the planning phase for the layout. We are creating a layout, and for the creation of this layout, the planning phase is known as floor planning. So, this is creating a floor plan is basically a way of conveying our intention or our intent about the physical design or the layout. Now, floor planning basically prepares the design for other physical design tasks, and therefore, it has got a huge impact on the figure of merit or F1, right. So, the rest of the design flow, right, from floor planning onwards, for example, the placement, the clock tree synthesis and routing, those will be highly impacted by what decisions we make during the floor planning stage, and therefore, floor planning is very, very important. Now, during floor planning, we must consider routability of our design, performance, power, and of course, during floor planning, we must pack the entities as compactly as possible. Now, what are the major tasks that we need to carry out during floor planning? The first is to define the die size or chip size and the aspect ratio of the die or chip. The second is placing IO cell or input output cell. What are these IO cells? We will see in subsequent slides. And then there are we need to place hard macros or blocks during floor planning stage. And then there is a task called pin assignment, which needs to be carried out during floor planning, and also we need to create rows for standard cell. Note that we are not placing standard cells, we are just saying that where the rows of the standard cells will be on the layout during the floor planning phase. So, we will look into all these tasks in some detail in the subsequent slides. So, the first thing that we need to do when floor planning is to decide the die size, or we need to choose the smallest size of the die that can fit the design. Now, why do we want to choose the smallest size of the die? So, the reason is that if our die size is smaller, right, then on the same wafer we can have more dies, right, and therefore, the cost per die of a chip will come down, right, and therefore, we should have the die size as small as possible, right. And the other thing is also related to the yield, right. In from the earlier discussion you might remember that yield is kind of inversely proportional to the area, meaning that if area of a die goes down, then the yield goes up, right. And therefore, we want to reduce the area of the die, so that yield can be moved, right. And therefore, we will be saving on the due to yield gains also if our die size is smaller. Now, what are the restrictions on the die size, right? We can make it smaller and smaller and smaller, but how smaller, right? The lower limit on the die size will come from that what entities we want to place on our die, right? We must while deciding the die size, we must include the area of the major components that will be there on our layout, right. So, in this figure I am showing a very simple kind of layout. Do not take it as we have this is a typical layout, but a simple layout in which I am showing various components that can be there on our layout, right. So, the components that can be on our layout and for which we must allocate space on the die, those are first is the IO cells or input output cells or IO pads they are also called. So, we must allocate space for this, right. So, this is the space we are saying we must allocate for the IO pads, right. The blue one, the blue area that we have shown, that we are say allocating for the IO cells or input output cells through which the signals will come to our chip or die, right. Now, the other entity is the standard cells, right. So, the standard cells that is in our design, that must be placed on the layout, right. So, we must allocate space for the standard cells, and standard cells we typically put in the rows, right. So, these are the rows of standard cells that we must think that we need to allocate space for that, right. Now, what should be the area of this space? So, when we are doing floor planning, by that time we have already got the net list, right. So, from the net list and using the libraries, the technology library, we can get that what is the area of the standard cells, total area of the standard cells, and that will give us that at least how much space we must allocate for the standard cells, right. Similarly, we will have macros. So, macros can be a hard macro, meaning that there can be memory elements or so on, or these macros can be say the blocks, right. This is a top level entity, and on this there will be blocks that we have got after partitioning, right. So, we must allocate space for the blocks and macros, and sometimes we need to also allocate space for hello. So, around the macro we say that there is a sub region where we do not allow anything to place, right. So, those becomes some area around the macro where nothing is allowed to be placed, and as such that area must also must be accounted when we are deciding the die size. Now, why we are allocating this hello or empty space around the block, we will see that in the subsequent lecture. And the final thing is the interconnect, and this is the most interesting or most difficult or challenging thing for floor planning. So, when we are doing floor planning, we have not yet done the routing, right, but still we need to allocate space for the routing, right, and or the interconnects that will be connecting various entities on our chip or on the layout. Now, how to do that? Because we have not yet made the layout, we do not know that what the interconnect area will be required, right. But before starting the floor plan, the physical design, we must know that what is the die size, right, and therefore, this is a challenging task, we have to do some estimate, right. So, typically we use a measure which is known as utilization to allocate some portion of the layout to the interconnects. So, what is utilization? So, utilization is the ratio of the cell area, right. So, if we consider this core, so the area of the die that is left after we have removed the portion of IO cells is the core. So, this is the core area, right, which is shown in pink, right. So, this is the core area, right. Now, in this core area, what entities are sitting? The standard cells, macros and the halos, right. So, if we take all this ratio, all these entities and take the total area and divide by the core area, that is the area that is shown in pink, we get that how much extra space is left for interconnects, right. So, if we divide, we get the number which shows that how much utilization we are doing, meaning that if we are saying that there is 100% utilization, then no space is left for interconnects, right. Ideally, we will want that situation. We will want that all the interconnections of the entities can happen over these entities. Note that the connection is done in layers, right, and in industrial designs we have 10 to 12 layers of interconnects available. So, ideally we will want that all the interconnections are done at the higher levels of metal and over standard cells, over the macros and so on, and all the routing are done over these entities, and we need not allocate any space for the interconnects, extra interconnects, right. And in that case, utilization will be 1 or 100%, right. We want that is the ideal situation, right. But in that case, finding a feasible solution will be very difficult, right, and the routing can fail at the when we do say the detailed routing. At that time, the tool may say that I do not have sufficient routing resource to do the routing, right, and then we need to again go back to floor planning and other chip planning stage and allocate extra space and so on. So, therefore, during the initial stage itself, we allocate some portion to for the interconnect, and we say that the utilization is rather than 1, we say that it is something between 0.6 to 0.8, right. Typically, we use these numbers, and this number will basically come from say the previous designs, right. Previous designs will say give us some kind of number based on which we have a good number or good estimate of the utilization, and which we have used in closing or achieving design closure in the previous designs, right. So, from the previous designs we can get some good estimate for the utilization, and we can move forward, right. And also we should understand that the die size is also determined by the package size, or it is very strongly dependent by it strongly depends on the package size which is available to us, right. So, the package size and its aspect ratio many a times that decide that what should be the size of our die. So, once we have decided the size of the die, its aspect ratio, the next part comes that the deciding the locations of the IO cells. Now, what are IO cells? So, IO cells are special circuit elements through which a chip communicates with the external world. So, the external world will communicate with our chip or through some pins, right, or through some cells or special cells. So, those cells are known as IO cells, they are also known as IO pads, right. So, these IO cells can be of many types. It can be of say input type, it can be of output type, or it can be of bidirectional type. So, in this figure I am showing you a bidirectional IO cell, right. So, in an IO cell there is a metal, this M pad which I am showing, this is a metal through which a connection is made, right. So, from this metal the wire will go to the package, that will show in the next slide, but understand that this is the IO cell, right, and inside this IO cell there will be some metallic pad, right, through metallic contact. From this the wire will go to say one buffer and another buffer, right. So, there are two buffers. So, whenever there is a signal, there is a signal which is OE which is coming from the core. OE is output enabled. So, if OE is equal to 0, this tri-state buffer is in high impedance state, right. This is a high impedance, we can consider that it is an open circuit, and in that case this IO cell will work as an input cell, signal whatever will be coming at the input, that will be going to through this buffer x1, it will go to our code logic, right. And if OE is equal to 1, right, OE is equal to 1, meaning out 1 is equal to enable, then this IO cell will work as a output cell, right, meaning that whatever will come from the core, whatever the value 0 or 1 will come from the core, that will be available at this MPAD, and that signal can be read by the external world, right. So, that is why this is the IO cell that I have shown here is a bidirectional IO cell. Now, what are the functions of IO cells? So, the one of the functions we have already seen, right, that it communicates with the external world, right. Other than that, there are other functions of the IO cells, the most important being the drive capability, to enhance the drive capability. So, typically the cells that are driving, say from the core logic, that is coming from core logic, those cells may not have sufficient drive capability to drive the load that will be driven at the output of this line, right. And therefore, these buffers that are there in the IO cell, those buffers must enhance the drive capability, right. So, the IO cells typically enhance the drive capability using buffers or a chain of buffers, right. Then there can be voltage transformation also, right. So, these IO cells can also work as level shifter, meaning that the signal that is coming from the external world may be at some other voltage level, and our core logic may be working at some other different level, right. So, the IO cell can provide this voltage transformation between these two entities. Then third important and very important function for the IO cell is that it gives protection to our circuit, right. What it means is that while we are handling our chip, right, when we are handling our chip, we may touch the pins, or even the machines can touch the pins, and because of that there can be an electrostatic discharge. What is an electrostatic discharge? So, electrostatic discharge is a short duration, very high voltage pulse. It may be several kilovolts, right. So, you might have seen this electrostatic discharge maybe while you are touched, say the handle of a door, and you got a certain shock, right, and that happens because there was a charge transfer between our body and say the door handle, and that through the ground and so on, right. And therefore, these when we handle the chip either through machine or manual handling, there accidentally this electrostatic discharge event can happen, meaning that as a very high several kilovolt pulse can be generated, but for very small duration, right. And if we allow that very high voltage to go to our core circuit, right, our core circuit element gates, that those transistors, that those may get damaged. So, IO cell will have some circuit element not shown in this figure to prevent the electrostatic discharge to penetrate our penetrate and reach our core circuit. Now, how are these IO cells connected to the package, right? So, let us understand it. So, this is the core, this is our die, right, this is our die, right, and these blue elements, these are IO cells, right, these are IO cells. Now, we saw that in IO cells there was a metallic element MPAD. So, that MPAD, from there the wire will go and will connect to the package pin, right. So, there is a package pin, these are package pins that are shown here, these are package pins, right. So, when we think of a chip, we look into the to the end, and there we see that there are some pins, right, for a chip. So, those are the pins of the package, and that is what we are referring here as package pins. And those package pins are connected to our die through these wires, these metallic wires, or these are known as bond wires, and these bond wires are finally connected to MPAD in the IO cell that we saw in the previous slide, right. And through that the signal will go through to the core logic, or the signal will go out from the core logic, right. Now, there are other kind of there are some kind of IO cells which serve the purpose of bringing in power and ground lines to our cores or to our circuit, right, and those are known as power pads. So, power pads are special cells that supply power to a chip, right. For example, this is the pin of a chip which is VDD, right. So, from here the power is coming and this will go to this IO cell, and this IO cell will be a power pad, right. Similarly, there will be a ground pad, for example, this is a ground pad, right. So, these power pads must also be placed on our die. So, functionally these power pads are just providing contacts with VDD, nothing else, right. Now, another thing to note is that the IO cells also need power and ground connections, right. So, for example, if you look into the power pad here, now these power pads contains buffers and other circuit elements, and those will also need a power supply, right. These buffers will also need a power supply, which is not shown here, right. You will have ground line and VDD line and so on, right. So, the IO cell also needs power supply. So, typically what we do is that the power supply of IO cells are kept separate. Why? Because IO cells draws a large amount of current. It needs to drive larger capacitors, and therefore, large current transient can occur in these IO cells, and therefore, there can be voltage fluctuations, right. And if those voltage fluctuations reach our core cells, then core logic gates, then probably those logic gates can malfunction, right. And therefore, we try to keep the power supply of the IO cells separate and the power supply of the core cells separate. Now, how many number of power pads should we have, right? Now, power pads are supplying the current to our chip, right, and therefore, the number of power pads that we need will depend on how much current is being drawn by our circuit, right. So, depending on the power drawn by our chip, right, or the current drawn by our chip, and what is the maximum current limit for an for a power pad, we can decide on the number of the power pads that will be needed. For example, if the current drawn by our chip is large, then we will be probably needing more power pads in our circuit. And also it depends on the target voltage levels, right, how much we allow the voltage level to be fluctuating in the core for the core logic gates. If the margin of fluctuation is smaller, then probably we will be needing more number of power pads that must be supplying power to our core cells, right. Now, how do we place these IO cells, right? So, in the floor planning stage, we also need to decide the locations of these IO cells, right. Note that these IO cells are basically designed, and those are characterized, and they are put in the technology libraries, right. So, IO cells are available in the technology libraries, and the tools can instantiate appropriate appropriate IO cells in our netlist based on the current requirement, drive capability, and so on. So, the IO cells will be available in our netlist, or we can instantiate them in our netlist, right. But then the second task is that where to place these IO cells on the layout, right. We need to decide that also, right. So, typically it is guided by some heuristics, Now, a few examples of heuristics can be like assign nearby positions to primary inputs that jointly drive a multi-input gate. For example, if two inputs are driven by the primary input, then probably these two primary inputs should be placed close together, or the IO cells corresponding to these inputs should be placed close together, a very simple heuristic, right. Then there can be the other heuristic can be to spread power hungry IO cells all over the die, right. So, to avoid creating voltage drop hotspots. So, if we put power hungry IO cells close together, then that area can become a voltage drop IR drop or hotspots, right. Now, what are these voltage drop hotspots or IR drop hotspots? We will see in when we will discuss power planning, right. But at this point we can just say that if we expect that the IO cells, two IO cells will be drawing large amount of current, or then we can put those IO cells further apart. That is one of the heuristics we can use while placing IO cells. The third heuristic can be that we can avoid placing sensitive signals such as the clock lines close to the IO cells. Why? So, the IO cells, as I have said, draws large amount of current, right, and if there are large amount of current, then these are in the vicinity of IO cells there can be large spikes, right, and those spikes can create signal integrity issues. And if the adjacent line is sensitive, for example, if it is a clock line or reset line which are more sensitive, or we want to make those signal more cleaner, we should keep those signals away from this IO cells which are expected to draw large transient currents, right. Now, one point that you should note is that the way that we have shown here, the way the IO cell that are connected here to the package pin, right, through through the bond wires, this is one type of package. Okay, so this is bonded wire package, right. So, this bonded wire package, right. Now, for CPUs and advanced chips or high performance chip, we use another kind of packaging, and that is known as flip chip technology. Now, in flip chip technology, what we do is that we have bumps are basically metallic connections, and those are at the top level of the die, right. So, at the top level we will have metallic bumps at multiple locations on the layout, right. And while packaging, what we do is that we flip the die upside down and allow that bump to be soldered into our package and allow that bump to make connections, right. Now, if our inputs and outputs can come even at the middle of our chip, right. For example, suppose this one was our die, right. Now, in the flip chip technology, the bumps can be anywhere, right, in the middle also, and the IO cells can be in the vicinity of these bumps. So, therefore, what it means is that IO cells need not be only on the periphery of the chip, as I have shown here. It can be inside the layout also, right. And if that is the case, we have more flexibility on putting IO cells close to the place where it is used, right, and therefore, the timing and other attributes of our design can improve, right, by putting these IO cells closer to the place where the connections is or input or output connection is actually required for the die, right. So, this is another thing which you should note, right. So, now if you want to know deeper into the topics that we discussed today, you can refer to this book. And to summarize, in this lecture what we have done is that we have looked into some aspects of chip planning. So, we looked into what is a hierarchical design flow, and in that what are the basic design steps that we need to carry out, and we looked a little bit on floor planning also. So, in the next lecture we will be continuing more with more deeper concepts of floor planning, and we will be also covering power planning. Thank you very much.